Hello, welcome to our last unit on logic. You'll notice in this unit there's more quizzes. I've broken up the material more to make it more digestible. So in this video, we'll cover Boolean logic and conditional logic, then move on next video to quantified statements. So these kind of statements you see in everyday language. You probably know them intuitively and understand how to evaluate basic statements. So you're like, why are we covering this? Well, when you start combining statements or making more complex claims, it's easier to get lost in the weeds and to be able to piece out the information into clearly labeled like structure, clear form, becomes a pretty powerful thing, especially when you combine that with the tool of truth tables to evaluate statements. So there'll be two quizzes on this. And then next week, we'll cover some more topics. De Morgan's laws of negating statements, complex statements, and evaluating statements using some of these tools, and then also identifying some common logical fallacies that you see. So let's jump in to Boolean logic. Okay, so George Boole at the middle of the 19th century was a self-taught mathematician and philosopher. He came up with some theory that laid the foundation for computer science using very basic ideas of combining statements either true or false. True, often represented by 1, false represented by 0. And he combined them with logical operators and or not. They sound very simple, but this is how zeros and ones, that's where information is stored on a computer. And this theory lays the foundation for modern computers. So you know how to use these kind of intuitively. Let's do a Google search for red and yellow triangles. Here's red and yellow triangle. Notice I get triangles that are both red and yellow, mostly. But if I search red or yellow triangles, Google is going to say, hey, you want either red or yellow, or maybe both. This is called inclusive. This is red or yellow. It's yellow. This is also red or yellow. It's red. But you see the difference generally in what Google will find. So here's another example. Suppose I like mystery and comedy movies, but I don't like Halloween. What would I search for on Google? I would go mystery and comedy, but not Halloween. The way we do that is minus Halloween. Creepy. So that's how I would get videos of that classification. So maybe I want to learn more about George Boole. Here's another example. What if I want to know what George Boole himself wrote about logic? What would I search for? George Boole or George Boole and or George Boole not logic. In this case, we would do and. I want to know both. I want to have results that satisfy both conditions. It talks about logic and it's George Boole. So these Boolean operators and or not are also like common ways to analyze sets. So a set of numbers 1 through 10, 1 through 9. Oh, this is an error here. Let's say 1 through 10 that are even. All the numbers that are even that satisfy that condition are 2, 4, 6, 8, 10. And I'll put brackets around them to help me know that this is one self-contained set. Divisible by 3 would be 3, 6, 9, 12. Oh, not 12. And now if I want to combine, if I call this set A and this set B, if I want to say even or divisible by 3, I need to find the guys that are in either set. So 2 is in either set, 3 is in either set, 4 is in either set, 6 is in either set, 8, 9, 10. So I'm just jamming those sets together. This whole set, each number in that set satisfies. It's either even or divisible by 3. But what if I want to say even and divisible by 3? Then I got to find which items are in both sets. Basically only 6. So that's how we use logical operators with sets. And you may be familiar with the set operators that are actually Boolean operators on sets. So if you see the union here, we can write two sets. This was A union B. It just says, I want to know all the other elements in either A and B. The intersection is elements in both A and B, so this would be A intersect B. I'm looking at the elements that are in both A and B. And complement would be the elements that are not in a set. So what if I wanted to do B complement? I would consider my universal set 1 to 10 and say everything that's not divisible by 3. 1, 2, 4, 5, 7, 8, 10. Okay, so we've expressed these statements using set operators. Okay. So I think we'll go over these in class. I'll give you some quicker questions in class, and let's do some conditional logic now. Okay, another kind of statement, conditional logic. So to go back a little bit, what is a statement in terms of logic? It's a sentence that is either true or false. It can be evaluated as true or false, also called a proposition in some contexts. And so a conditional statement is if P, then Q, or if P, else Q. And so logically, we would write this if P, then Q, as P arrow Q. P implies Q. So here we go. Common language. If it's raining, we'll go to the movie. Otherwise, we'll go to the lake. Often we see conditional logic in spreadsheet applications using, like when you see an equal sign in Excel, that means I'm going to type a formula. And if I say if, here's my statement, that's a statement that's either true or false. Here's my cell A1. And in that cell A1, there's some value. This evaluates it. If it's true, the first output is this. If it's false, the second output is that. So if A1 is 1,000, what's going on in A1? If A1's 1,000, this cell here is going to output, it's going to say, hey, is A1 less than 1,000? Yes, true. So it's going to add 1 to 1,000. Well, here's another example. What if A1 is 4,000? Then this cell here is going to evaluate, hey, 4,000, is it less than 2,000? No, false. So the alternate statement is A1 times 2. So we'll multiply that by 2 is 8,000. That's a way you can see conditional logic operating in something like a basic spreadsheet. But, oh yeah, so it's also in many other ways of talking. So we got if P then Q. Let's use the language where P is my hypothesis, something that I'm not sure it's true, but if it is true, then Q, the conclusion, is going to be true. Okay, so that's the same thing as saying this is equivalent to Q if P. Just flip it around, right? But what about this? All P are Q. So if it's P, then it's Q. So everything that is P also has the condition Q. So that's an equivalent statement. Here's another equivalent statement. No P are not Q. So if it's not P, so every P is Q, right? So then no P cannot be Q. It's kind of, we'll see later, these are quantified statements, why these are the same thing. But that's something you'll hear. What else? Okay, P is sufficient for Q. That's an equivalent statement to if P then Q. It's saying if I want Q to be true, all I need to check is if P is true, then Q is true. If P, then Q. So that's one way of writing it. And one more way you'll see is Q is necessary. Or P, unless I flipped them. So this says if P is true, then Q must necessarily be true. So these are all phrasings of the exact same conditional logic, if P, then Q. So you can see this comes up in many contexts, and then we can start to apply it to statements. And that's what we're doing in 2 videos from now. Okay, so we'll see you in the next 2 videos shortly.